In my last video, we looked at sketching graphs. In this video, we're going to move on and look at transforming graphs. We're going to look at three different types of transformations. They're translations, reflections, and stretches. We'll work through the theory behind each and then apply them to a range of different functions. We're going to start off with translations. So if we're translating a graph, we don't alter its shape, we simply pick the graph up and move it. We're going to consider two different types of transformations, one in the y direction and one in the x direction. So the first one we're going to look at is the f of x plus a. This is in the y direction and we can represent this with a vector of 0a. Let's take a function. Let's say we got the f of x is equal to x squared. So this gives us our standard parabola with the minimum point now at the origin, or if you like, the vertex at the origin. So we're going to be opening upwards and it will look something like so. All we're going to do, if we apply the translation of the f of x minus a, we're simply going to move this now up or down the y-axis. So let's consider now the f of x plus 1. This gives me now a translation vector of 0, 1. So all I'm going to do is pick the graph up and move it up by 1 unit. So if we look at that, this point is going to be 0, 1 instead of 0, 0. Same shape, no alteration in the shape, and then we'll come up like that. Let's consider what I've just done in terms of the equation. So what we've got then, let's say y is equal to x squared. That's our original function. So when x is equal to 0, y is going to also be equal to 0. Let's now look at y is equal to x squared plus 1. So all I'm doing is adding 1 to my function. If x is equal to 0, 0 squared is 0 plus 1, y is going to be equal to 1. Often if you consider a point and where that's mapped to, it makes transformation significantly easier. Students are sometimes guilty of just learning a set of rules, yet in reality not really grasping what's happening to a given point on a graph. If you do, it will make it fairly straightforward. So that's an example. If we had now the f of x plus, in fact we'll go for minus 3. This now will be 0 minus 3. So we would move the graph down, the original graph, to this point right here, and that would be 0, minus 3. And as you can see, all we've got here is y is equal to x squared minus 3. So when x is equal to 0, y is going to be equal to 0 squared minus 3, y is equal to minus 3. That now gives us a translation in the y direction. Where we can see now the a, this is on the outside of what we call the argument. This is the argument, x is the argument. If it's on the outside, it's going to affect the y coordinates. If it's on the inside, it's going to affect the x coordinates. So the second translation we're going to look at is the f of x plus a. This is slightly less intuitive as it's now a minus a 0 translation in the x direction. So let's take the f of x again, and this is going to be x squared. So what we've got then is x squared. So we'll place this on like so. So that's x squared. So the f of x is equal now to x squared. Let's look at the f of x plus 4. This is going to give us now a translation of minus 4, 0. If we consider this point right here, this point is 0, 0. So if I put 0 in, I get 0 out. Let's look if I had now x plus 4 all squared. So we could say that y is equal to x plus 4 all squared. Consider now, if x is equal to 0, y is going to be equal to 4 squared, which is 16. So if I now consider when x is equal to minus 4 plus 4 is 0, y is going to be equal to 0. Hence, why we move this now in the opposite direction to what you expected. So this point now is minus 4, 0. So all we've done is move that across. We will see now that the curve comes up. There's no alteration in the shape, and this point is 0, 16. So we can see now we're translating the shape, we're moving it now to the left by 4 units. This is on the inside, the A is on the inside, therefore it's affecting the x coordinates. So if we had a look now, let's say we had the f of x minus 3, that would move the graph now to this point just here of 3, 0, and we'd end up with something now like so. So let's just sketch that up, and it would look like that. Now just think about this. All we've got here is y is equal to x minus 3 all squared. So if x was equal to 0, y would be equal to minus 3 squared, which is 9. And that gives us this point just here, which is 0, 9. Now if we took x to be equal to 3, then that's going to give us 3 minus 3, y is going to be 0. So to achieve the same y coordinate, we have to now simply move everything by 3 units to the right, as we're going to be subtracting that value away. In the same way, if we consider now if we move this 4 units, then we'd need to subtract away the 3 to get the same y value. So these are translations. No alteration in the shape. If A is on the outside, it's affecting the y. If it's on the inside of this argument right here, it's affecting the x. Let's now move this on and look at combining translations. So if I have now the f of x minus 2 plus 4, then what we're doing with this particular one is simply now moving 2 to the right and 4 up. If we had the f of x plus 1 plus 3, this one I'm going to move 1 to the left and 3 up. If we had the f of x plus 3 minus 4, we're going to move now minus 3 minus 4. If we had the f of x minus 1 plus 5, we're going to move 1 to the right and 5 up. So let's go ahead and take the f of x to be equal to x squared again. If I apply this one, what I have now is the following. I would have now the f of x minus 2 will be equal to x minus 2 all squared. So instead of evaluating x, I'm evaluating x minus 2 plus now 4. You might recognise this as the completed square form, and we've looked at completed square form. So this tells me that the minimum point now is at 2, 4. All we've got here now is this point. So this is 2, 4, and we've got now the parabola. The minimum point here is going to be 2, 4, and we can see that that is a translation of 2, 4. I've moved from 0, 0 up to this point right here, and that's the completed square form. So this one right here, now we would have x plus 1 all squared plus 3, and we know that that minimum point would be now minus 1, 3. So minus 1, 3 is going to be about there, as we're taking this to be the positive x squared. So now you can see in terms of the graph transformation how the completed square form just gives us these two simple translations in both the x and the y direction. So there we go, translations. We don't alter the shape of the graph, we just move it. They're translations. Let's move on and look at reflections. So reflections, as before, we've got two different types of reflections. The first one we're going to look at now is minus f of x. This is on the outside. The minus is on the outside of this argument, therefore it should now be affecting the y coordinates. Let's go ahead and take the f of x to be equal to x squared again. Using this particular graph is fairly straightforward, as we can see now how points work. So what we'll do then is define f of x is equal to x squared. So in this case, we're going to have our parabola, we're going to have 0, 0, and it'll look something like that. Let's go ahead, put this point 1, 1, let's put this point 2, 4. What we're doing here is minus x squared. So we evaluate 1, 1 squared is 1, then make it negative. As a result, we reflect this in now the x-axis. So we get the point just here, and that point is going to be now 1, minus 1. If we put 2 in, 2 squared is 4, times it by minus 1, we've got now 2, minus 4. So we can see it's on the outside, it's now affecting the y coordinates. So this is a reflect in x. Now you might say, well, that's not the case. If you reflect it in the x-axis, you're actually reflected in the line y is equal to 0. So a couple of different ways of looking at it. Okay, let's look at the next one, the f of minus x. Now this should therefore be a reflection in the y-axis. It's on the inside, so it's going to affect the x-coordinates. Okay, let's take an example of this. What I'm going to do, I'll let you do if you really want. If you want to do x squared, if you want to hit pause, you can do, and you'll see why this is probably better if we do it with a different graph. Okay, let's go ahead and do the following thing. So what I'm going to have then is y is equal to x cubed. So y is equal to x cubed, or we could say now the f of x is equal now to x cubed. Let's take this point just here, and we'll have 1, 1. Let's have this point just here, 2, 8. Let's have this point just here. That's minus 1, minus 1. And let's do minus 2, minus 8. Okay, now what I'm going to do is the following. I'm going to put the value in and multiply the x-coordinate by minus 1. Therefore, I'm going to put in here now minus 1. So instead, what am I going to end up with? Well, the answer is quite clearly minus 1. So if I do now, let's put that in. If I put 1 into the function and we do minus 1, we're going to get this point just here, which is going to be 1 comma minus 1. If I put 2 in, minus 2 is going to give me now 2 comma minus 8. If I put minus 1 in, well, that's going to give me positive 1, and I'm going to end up now with minus 1 comma positive 1. If I put minus 2 in here, minus 2, the negatives will cancel out, so I'm going to get 2 comma, minus 2 comma positive 8. And you can see now that this is going to be a reflection in now the y-axis. It's going to be now inside, so it's affecting the x-coordinates. We can see the y-coordinates are staying the same, the x, the sign has changed. So this is a reflection in the y-axis. If it's on the inside, it's going to affect the x. If it's on the outside, it's going to affect the y. So all I've done is taken those particular values, I've multiplied them by minus 1 and evaluated the graph or the function as such, and then just gone ahead and done them. And that's nice and straightforward. And quite clearly you don't always have to do those points. So if we looked now, let's take another function. Let's say a function, let's take a graph. Y is equal to 1 over x. So this is now our graph. So let's do now the f of minus x, and let's do now minus f of x. So what's this going to do? Well, we know the top one now is going to reflect this now in the x-axis, in the y-axis, and then the bottom one will reflect it in the x-axis. So our original graph, 1 over x, and I just have to, let's just put this here, let's write this here, the f of x is equal to 1 over x, and I just have to write that x cannot be equal to 0, just to make sure it's now a function, because it's not defined here as we've seen before. So this is a graph that we've got. So this is now 1 over x. We can't do 1 over 0, as we hopefully realised in the last video. So what I've got here now is a reflection in now the y-axis. So if I get my reflection in the y-axis, let's just put a circle around here, we're going to end up with the following. So it's going to look something like that, and then we're going to have something now like so. Okay, so that's a reflection. And now the next question is, what's the other one going to look like? Hopefully you can see that is going to do exactly the same, and we'll simply have the same again. And that's a quirk of that particular graph. So again, just be careful. We've got no alteration in the asymptotes of these. Let's just go ahead and put those on. So asymptotes, we won't see them because they'll be hidden by the coordinate axis. But that's what we end up with. So we reflect it in the y-axis, and again, this point right here. Let's have a look at this point right here. So now if we put here, this is going to be 1, 1. If we consider now, this point is going to be 1 comma minus 1. And exactly the same here if you did that. So they are two of the same. So reflections. Okay, let's move on to the third sort. And the third sort are stretches. And stretches are the ones pupils dislike the most. The first one is AF of x. Now, this is a scale factor stretch in the y direction of A. So let's think about this logically. It's on the outside, so we know if it's on the outside, it's going to be affecting the y coordinates. What I'm going to do is the following. We're going to have now the f of x is equal to x squared. So let's take the f of x. So the f of x is equal now to x squared. What I'm going to look at is the following. So here's our parabola. We should be fairly happy with this now. We're going to have this point here, 1, 1. We're going to have this point here, 2, 4. We're going to have this point, 3, 9. Let's say now I do 2f of x. So what's 2f of x going to do? Well, if I do now 2 lots of the f of 1, now the f of 1 is going to give me 1. The f of 2 is going to give me 4. The f of 3 is going to give me 9. So what I need to do is multiply this 1 by 2. I need to multiply this 1 by 2. And I need to multiply this 1 by 2. As a result, what we're going to end up having is this point just here. We're going to have 1, 2. We're going to have this point right here, and I'll put that there, 2, 8. We're going to have this point here, which will be 3, 18. As a result, we end up now getting tighter and tighter to now the y-axis. So this is a scale factor stretch in the y direction, and we end up now with a tighter curve to that axis. Now I'll let you think about what happens if we end up with a value here. See, I've taken a to be greater than 1. So if we had now, let's consider a, let's say a was between 0 and 1. Let's think about 1/2 f of x. This is going to give us a scale factor stretch of 1/2 in the y direction. So if we now think about this point right here, we're going to end up with 1/2. We're going to have this point, and that's going to be now 2, and I'll just jot these on, 2, 2. We're going to have this point right here, and that's going to be 3, 9 over 2. So you can see, I mean, obviously I've put these out not where they should be as such, but we're going to end up now opening that up more. So this now is a scale factor stretch, so SF of A in the y direction. So direction. So you can see that it's now the y coordinates. Again, it's on the outside. It's the y coordinates that are going to be influenced by this transformation. Okay, the next one is probably the one that, again, is very counterintuitive. The f of ax. This now is so a scale factor stretch of 1 over a in the x direction. And what I want you to do is just hit pause now to think what this means. A 1 over a scale factor stretch in the x direction. And what I want you to do is consider when a is going to be greater than 1 and when a is going to be between 0 and 1. You might want to take now the following. You might want to take just x squared. So hit pause, have a go at it and see what that does for you. Right, okay. So hopefully you've got some understanding of what's gone on. So we know it's on the inside, so it's going to be affecting the x coordinates. Let's have a look at the f of 2x. So we'll take our original graph. The f of x is equal to x squared. So let's go ahead and think about some points on this. So let's go ahead and do that. So parabola, we know now. And as you can probably imagine, in both of these cases, 0, 0 is an invariant point. That means it doesn't move, because quite clearly if we multiply 0 by anything, it's just 0. So we've got 1, 1. We've got now 2, 4. We've got 3, 9. Okay. So what would happen now if I did the following? If I did the f of 2x, then what we'd have now is the following. I know that the f of 1 gives me 1. I'd multiply this now by 2, which would give me 2, and then I would end up now with the following. So I'd end up with the point here, so subbing in 1. I'd do the f of 2, that would give me now the value of 4. So we could go ahead and plot that point. Now, if you think about what's happening here, let's go ahead. This point is going to give me now 1, 4. Because I put 1 in, I times it by 2, I square it. And that's going to give me 1, 4. What I'm going to do is just put up another point just here to kind of get you understanding, hopefully, of this. Let's put this point 4, 16. Now, if I put 2 in, 2 times 2 is 4. 4 squared is 16. So this point now is going to move to 2. So let's put this just here. Let's grab the red one up rather than here. This is going to give me 2, 16. So let's look at the relationship now. Before, I needed 2 to go in to get 4. I only need 1 to go to get 4. I needed 4 to get 16. I only need to get 2 to get 16. As a result, we have this stretch of 1 over a. I'm essentially dividing the x-coordinates by this value of a. So 2 has gone to 1, that's 2 divided by 2. 4 has gone to 2 to give us the same value. So this is a 1 over a. So if we had, for example, now 6, all I'd need to do is 3. So we can see now that it's a 1 over a scale factor. And that's when a is going to be greater than 0. So if we did the f, let's do the f of 1/2 x. Now consider what we would have. We would have the point, and let's take this point right here. If I have now 2, I put 2 in here, that's going to give me 1 squared, and we'll put it on here. So let's put that there. 1 squared is going to be 1. So what I'm going to get is this point, 2, 1. If I put 4 in, I'm going to get 4, which is going to be just here, and that's going to give me 4 divided by 2 is going to give me 2. So I'm going to get 4, 4, and that's going to be, let's put that there, 4, 4. What we're going to see with this is now that it's going to be now, let's just get some form of, there we go, it's going to be more widely open. So when we've got now our value of a, it's actually moving out. So it's kind of counterintuitive because it's working in essentially the opposite direction. But if you take a point on the graph now, it's fairly straightforward. So let's say now, let's just generate some particular function right here. Let's just do some positive values. Let's say we've got now the following, and we've got this. So what we would do now, let's see what we can do. Let's say this point is going to be 0, 1. Let's say that this is going to be 2, 0. Let's say that this point is going to be 4, let's say that's going to be 4, 3. Okay, so if we look now at the f of 2x, then what we're going to have then is this point right here. So all we would need for that one now is 1, and we'd end up with 0. If we now looked at this point right here, we would end up needing 2. So we'd end up with now a scale factor stretch. So we'd be simply halving the x-coordinates. So that would be 2, 3. And we'd end up with it looking something like so. So this point stays where it is because half of 0 is just 0. But we'd now have this stretched now inwards. Yet if we had the following, if we had now f of 1/2 x, then consider what we'd need to do. We'd need to now go to 4 to get 0, because it would be now down to 2, which gives us 0, and we'd need 8, and let's put 8 just here, to get the value of 3. So let's put that way out there, and that's going to be 8, 3. So with this one, let's put that on, we'd need to stretch it, so it's going to look something like that. So we can see now how these alter it. So that gives us a stretch. So again, with our value of a, if it's on the outside, it's going to affect the y-coordinates. If it's going to be on the inside, it's going to affect the x-coordinates. And just picking a point is often significantly easier than trying to remember these particular rules. 1 over a in the x direction if we have f of ax, and then scale factor of a in the y direction if we have af of x. If you're ever stuck, just take x squared and consider a couple of points, and it should lead you to thinking about how these functions operate and what happens if you now multiply the values of them. In the next video, what we're going to do is just work through a range of basic examples and actually apply these to particular functions. We've looked at some of the theories, we've looked at the stretches, we've looked at the reflections, and initially the translations, and then we'll put those all together when we come on to some questions relating to the transformation of functions.